International Physics Olympiad year 1984 IPHO. Problem number 2. Seiching. In certain lakes there is a strange phenomenon called seiching, which is an oscillation of the water. Lakes in which you can see this phenomenon are normally long compared with the depth and also narrow. It is natural to see waves in the lake, but not something like the seiching, where the entire water volume oscillates like the coffee in a cup that you carry to a waiting guest. In order to create a model of the Seiching, we look at water in a rectangular container. The length of the container is L and the depth of the water is H. Assume that the surface of the water to begin with makes a small angle with the horizontal. The Seiching will then start, and we assume that the water surface continues to be plane but oscillates around an axis in a horizontal plane and located in the middle of the container. Create a model of the movement of the water and derive a formula for the oscillation period T. The starting conditions are given in figure above. Assume that C much less than H. The table below shows experimental oscillation periods for different water depths in two containers of different lengths. Check in some reasonable way how well the formula that you have derived agrees with the experimental data. Give your opinion on the quality of your model. The graph below shows results from measurements in Lake Vättern in Sweden. This lake has a length of 123 kilometers and a mean depth of 50 meters. What is the time scale in the graph? The water surface level in Bastudalen, north end of the Lake Vättern, and the Jönköping, southern end. Solution for problem 2. In the coordinate system of the figure, where point 0, 0 right in the middle of this figure, we have for the center of mass coordinates of the two triangular parts of the water. For the right triangle we have x1 equal L over 3, y1 equal h over 2 plus c over 3, and for left triangle we have x2 equal negative 3 over 2 and y2 equal h over 2 minus c over 3. So for the center of mass coordinates will then be x center of mass, it's xcl over 6h, and y center of mass c square over 6h. Due to that the y component is quadratic in c, will be much smaller than the x component. The velocities of the water mass are this one, if we take first derivative by time from this first equation. And again the vertical component is much smaller than the horizontal one. We now in our model neglect the vertical components. The total energy, kinetic plus potential, will be this one. For a harmonic oscillator we have this expression. Compare these two expressions, we can identify omega as square root from 12gh over L, or period T will be pi L over square root from 3gh. Our model gives a slight underestimation of the oscillation period. Applying our corrected model on the water data, we have that the oscillation period of the Seiching is about 3 hours. Many other models are possible and give equivalent results. That was solution for problem number 2.